Why is antimatter considered the key to interstellar travel? Once antimatter technology is mastered, a spacecraft could be accelerated to 70% of the speed of light. Over the past few decades, the images sent back by the Voyager probes from Jupiter and Saturn made it feel as if humanity conquering the universe was only a matter of time. But what you may not realize is this: space exploration has never been a romantic voyage among the stars. It is a life and death struggle against the laws of physics. We didn't just underestimate the difficulty of the technology, we ignored the most brutal red line between Earth and the stars: energy. Have you ever wondered why we can build high-speed trains that travel at 350 km/h and supersonic fighter jets, yet can't build a spacecraft that can casually fly out of the solar system? The answer lies in a force you experience every single day, but rarely stop to think about: gravity. Let's start with a simple thought experiment. Pick up a ball and throw it hard into the sky. It flies upward, slows down under gravity, and eventually falls back to the ground. The harder you throw it, the higher it goes. But no matter how hard you throw, it always comes back. That is Earth's gravity. And the only way to break free from this shackle is to reach an orbital velocity of 7.9 kilometers per second. At that speed, a full lap around Earth's equator takes just 90 minutes. And if you want to completely escape Earth's grip and head into deeper space, you must exceed the second cosmic velocity, 11.2 kilometers per second. Only then can you truly break free of Earth's gravity. Probes like Galileo and Cassini left Earth at this escape velocity, but even so, they can only explore within the solar system, because the energy sources humanity currently controls are nowhere near sufficient to support the ambition of interstellar travel. Some might ask, can't we just develop more powerful fuels, like the leap from coal to oil, or from oil to nuclear energy? To answer that question, we must return to the very foundation of matter, the atom. For a long time, humans believed atoms were the smallest indivisible units of matter, that everything in the universe was built from these tiny blocks. But the physics revolution of the 20th century completely overturned that idea. Atoms can be split, and their internal structure is astonishingly complex. People once thought atoms were the universe's smallest Lego bricks, impossible to divide, until the early 1900s, when scientists discovered that an atom is more like a miniature solar system. At its center is a tiny atomic nucleus, surrounded by a fuzzy cloud of electrons. The nucleus is made of protons and neutrons. Protons all carry positive charge and should repel each other, yet they are bound together by a kind of super glue that only works over distances smaller than 1/10 billionth of a human hair. This glue is the strong nuclear force, and the energy stored in it is binding energy. It comes from a tiny loss of mass when protons and neutrons fuse together, converted into energy. According to Einstein's equation, E equals mc, the simplest way to release this glue energy is nuclear fission, splitting a heavy nucleus into two lighter ones. The lost mass instantly becomes heat and light. Control the chain reaction, and you get a nuclear power plant. Let it all split at once, and you get an atomic bomb. The mass-to-energy conversion efficiency of nuclear fission is only about 0.1%, but even so, the energy released is millions of times greater than chemical reactions. That's why atomic bombs are so devastating. Yet, even nuclear fission is still far too inefficient. For interstellar travel, humanity needs a much more powerful energy source. That leads us to the second path: nuclear fusion, the energy source of the sun and the stars. The sun has been shining for 4.6 billion years, and will continue to burn for another 5 billion. Every second, the sun fuses 600 million tons of hydrogen into helium, of which 4 million tons of mass are completely converted into energy, radiated into the universe as light and heat. Only a tiny fraction of that energy reaches Earth, yet it gave rise to life, drives monsoons and ocean currents, and allows us to exist. Humanity has been exploring nuclear fusion for decades. France's ITER project brings together the power of 35 countries, with the goal of building the first fusion reactor that produces more energy than it consumes. If successful, humanity would gain nearly limitless clean energy, and space exploration would undergo a qualitative leap. With fusion engines, we could reach Jupiter or Saturn in months, instead of years. But even today, controlled nuclear fusion remains a global challenge. How to confine ultra-hot plasma, how to maintain stable reactions. None of these problems have been fully solved. And to truly cross interstellar distances, such as reaching Proxima Centauri, 4.2 light-years away, we would need a way to convert 100% of mass into energy. That ultimate energy source is antimatter, the king of energy density, that could enable humanity to achieve interstellar exploration. When you hear antimatter, you might think of annihilation bombs from science fiction, but its real story begins with a bold idea from a brilliant physicist. In 1928, 26-year-old British physicist Paul Dirac faced a monumental problem in physics. Quantum mechanics and special relativity could not be reconciled. Quantum mechanics describes the microscopic world, where particles can exist in multiple places at once, where observation alters reality, and probability rules everything. Special relativity describes the realm of high speeds, where time slows, length contracts, mass increases, and space and time merge into one. Dirac's goal was to find an equation that could describe electrons moving at relativistic speeds, while still obeying quantum mechanics. It was an extraordinarily difficult mathematical challenge. After months of relentless effort, he finally found a mathematically perfect and symmetric equation, but it had a strange feature. It produced two solutions. The first solution described electrons with positive energy, the familiar electrons that make up everything around us, but the second solution pointed to electrons with negative energy. At the time, this seemed completely absurd. How could energy be negative? If negative energy particles existed, they could release infinite energy, violating the law of conservation of energy. After long reflection, Dirac made a daring hypothesis. For every matter particle, there exists a corresponding antiparticle. Protons have antiprotons, neutrons have antineutrons, and there might even be a complete antimatter universe. Just 2 years later, American physicist Carl Anderson confirmed Dirac's prediction while studying cosmic rays, high-energy particles from space, thousands of which pass through our bodies every second, without us noticing. He used a device called a cloud chamber, a sealed space filled with supersaturated water vapor, on the verge of condensation. When a charged particle passes through, it ionizes air molecules, forming tiny droplets that reveal the particle's path. The invisible quantum world became visible to the naked eye. Antimatter went from mathematical speculation to physical reality, and Dirac received the 1933 Nobel Prize in Physics. The most astonishing property of antimatter is annihilation. When an electron meets a positron, they instantly transform into two photons, converting 100% of their mass into energy. This is the most efficient energy conversion in the universe. 1 gram of antimatter, annihilating with 1 gram of matter, releases energy equivalent to 3 times the power of an atomic bomb. If antimatter could be used as fuel, human spacecraft would gain unmatched thrust. Reaching Proxima Centauri might take just a few years, instead of tens of thousands. But between dream and reality stand two nearly insurmountable mountains: production and storage. Antimatter no longer exists naturally. According to the Big Bang Theory, matter and antimatter should have been created in equal amounts. They annihilated each other, leaving only energy. So why is our universe full of matter? This is one of the greatest mysteries in physics. Scientists suspect that, in the brief moments after the Big Bang, a tiny violation of CP symmetry occurred, leaving matter with an excess of 1 part in a billion. That minuscule surplus formed stars, planets, and ourselves. Today, no naturally occurring antimatter exists on Earth or in the solar system. We can only manufacture it artificially. The only way to create antimatter is to reverse Einstein's equation, concentrating immense energy into an extremely small space to produce matter and antimatter. This is exactly what the Large Hadron Collider at CERN does. In 1995, CERN produced the first complete antihydrogen atom. In 2002, scientists generated 50,000 antihydrogen atoms at a rate of 10 per second. Today, they can trap antihydrogen atoms for hours to study their physical properties. But behind these achievements lies staggering inefficiency. The energy required to produce a single antiproton is 2.6 million times greater than the energy released when it annihilates. Producing 1 gram of antimatter would require several times the world's annual electricity output, at a cost of $100 trillion. Even with full global effort, we can only produce 1/1000th of a gram per year. To make 1 gram would take an unimaginably long time. An even more fatal challenge is storage. The moment antimatter touches any matter, it annihilates explosively. We cannot store it in metal, plastic, or any conventional container. The only option is to use powerful magnetic fields to suspend charged antiparticles inside a perfect vacuum, a magnetic bottle, without touching anything. But this method is extremely fragile. The magnetic field must be perfectly stable. Any power failure, slight collision, or gravitational disturbance would let the antimatter escape and trigger an explosion. Imagine a spacecraft carrying antimatter fuel, accelerating, decelerating, or passing through an asteroid belt. Any tiny malfunction could mean total destruction. This is the paradox of antimatter. It is humanity's ultimate hope. for crossing the stars, and also the most dangerous substance imaginable. Despite being the king of energy density, antimatter is something we cannot make, cannot store, and cannot afford to use. In theory, we hold the key to the universe's gate, only to discover that the key itself could destroy us. So should we give up? The answer is no, because the history of human exploration has always been a cycle of using the known to explore the unknown, from making fire to harnessing nuclear energy, from launching rockets to studying antimatter. The fuels change, but the essence of exploration does not. Antimatter may never become a practical space fuel, but the pursuit itself has already changed how we understand the universe. In trying to understand antimatter, we have touched the secrets of cosmic birth, grasped the deep link between matter and energy, and even begun to answer why the universe is not empty. Every failed experiment, every unsolved problem, brings us closer to the truth. Space is indeed more dangerous than we imagine, and the dream of the stars is far more distant than we once believed. The key of antimatter may never open the door to interstellar travel, but it has shown us both our insignificance and our greatness. The meaning of this pursuit has never been just about building a faster spaceship. It is about our willingness to challenge the limits of physics for a dream, to face unknown dangers head-on, and to rediscover who we are through the exploration of the universe. Perhaps even 1,000 years from now, we still won't reach another star, but we will have learned the language of the universe and understood the meaning of our existence. And that may be the ultimate answer to why humanity explores space, not to conquer the universe, but to find our place within it.